So today we're mainly learning about angle in circular relationships, how you can actually take any angle you've ever learned about and apply it to a circle and actually to understand the angle a little bit. So before we get going, we do have a couple of vocabulary terms that you're not familiar with that we just need to go over. The first two vocabulary learns I want us, or vocabulary terms I want us to learn are two different types of sides when you're talking about an angle. The first is the initial side, and the second is called the terminal side. These two sides of the angle are exactly like they sound. The initial side is the side you're starting from, and the terminal side is the side that you're going to and ending. So here on this angle, my initial side is always going to be, if I applied this angle to a quadrant plane, this would be our positive x-axis, or a 0-degree angle. This is our initial side. Your initial side is always going to be on the x-axis. Sometimes it will be the reverse, like this, and therefore the initial side would be on the negative x-axis. But it's always going to start on the x-axis. So this is our start. This is where we begin. That is awful. And this is our terminal side. This is where the angle ends. And between our two sides, of course, is our angle, our theta. And we're always measure angle from the initial side. No, initial side to terminal side. No, and you'll see in a bit why I consider the initial side um, as the x-axis, because when you're creating what is called your reference angle, you're always drawing a line downward to your initial side. So you'll see that in a second. And this right here is also our vertex. That's our vertex. If this is on a circle, that's like our origin. The initial side would represent, well, I mean, both sides actually would represent our radius. Okay, so knowing that, there are also two different angle types that you can have. You can have a positive angle. What was I about to write? I don't know. Positive angle. And you can also have a negative angle. Now, a positive angle is always an angle from your initial side going counterclockwise. Whereas a negative angle is always from your initial side going clockwise. So if I were to draw an angle here, and I'm telling you that this angle is 120 degrees, it's positive because from that initial positive x-axis to get to the vector that's creating our angle, we're going counterclockwise from the initial side, making it a positive angle. versus if I have the same exact angle, so the same exact uh, line here, the same exact vector, if I can get it. But instead of from our initial side, instead of going counterclockwise, we're now from this positive x-axis going counterclockwise. How many degrees would this angle be? Yes, exactly. So we know a hole all the way around all four of our quadrants is 360 degrees because they form a circle actually. So it's 360 degrees. We do 360 minus 120, we get to 240. However, I just said that because we're going clockwise, this is actually a negative angle. So it's negative 240 degrees is what we would say. Yeah. I'm so sorry. I just drank day old coffee. Oh my God. Oh my God. Ugh. I think I'm okay. All right. So we learned these vocabulary words basically so that we could understand what a coterminal angle is. They love to ask you for coterminal angles. Love, love, love to ask you what a coterminal angle is. It can be defined as different angle measures that share the same initial side initial and terminal sides. Sorry, I keep moving it. It won't bring that in. There we go. Initial and terminal sides. All you have to do to find coterminal angles is take the original angle and add or subtract 360 degrees or 2 pi, depending on if your angle in. And then also a little side note, you can find more coterminal angles, more by plus or minus, adding or subtracting, I'm just using that plus or minus symbol, adding or subtracting multiples of 360 or 2 pi, i.e. 720, 3 times 360, 4 times 360, or things like 4 pi, 6 pi, 8 pi, and multiples of 360 or 2 pi will give you a coterminal angle to your original angle. So again, I know there's a lot of writing here, but the main point of a coterminal angle is they're different angle measures, but they share the exact same initial and terminal side lengths, or sides of your angle. So let's try an example here for this 30 degrees. We're going to find two coterminal angles to 30. Now this isn't degrees, so I'm going to be dealing with 360 here, right? Do you guys, did I not explain that to you, that pre-cal is just like a mix of geometry number 2 on steroids? You'll learn. You'll get it. All right, so here, um, you're going to take 30 degrees, and we're going to find our co-terminal angle by adding 360 to it, and you get 390 degrees. So you draw the exact same line that a 30-degree angle would give you. You draw, now 30 is a third of the way through 90, so you know you draw it a third of the way. I've got this fancy little thing that tells me exactly where to put it, about. So this, if I was just going from the positive x-axis up to there, that would be 30 degrees. But I'm actually trying to show the coterminal angle of 30 degrees. So what you do is, we know that 390 is bigger than 360. So you're going from your initial side around, and then you keep going until you end on your terminal side. This is a coterminal angle to a 30-degree angle. Co means together, terminal means end. So they end together, basically. Then we're going to find another one. We're going to find, whoa, no. We're going to find another one by instead subtracting 360 degrees. So 30 minus 360 is negative 330 degrees. And again, you're drawing the exact same vector, that 30-degree angle actually. But instead of just drawing the 30-degree angle, we're going negative 330, meaning we're now going to be going clockwise. We're starting on the same positive x-axis, but we're now rotating clockwise around our coordinate plane to our terminal side. So you would say here that these are 3 coterminal angles. They all end on the exact same vector, just in different ways, right? This original 30 would have just been this. Well, I tried to be all quick about it. This is our 30-degree angle. So these are 3 co-terminal angles. Okay. Any questions on this one? Pretty straightforward, I think, just vocabulary. Now over here, this is a little bit more tricky, just because you've been taught all your math careers to think in degrees. I still mainly think in degrees. I mean, I don't even, and I've had many, many years of math. I don't know how people switch over to thinking in radians, but some people do. Some people think in radians, which is just fine. But we're going to pretend like we all think in degrees, which I think that you all do. So what we're going to do here is, we're first going to ask ourselves, we're trying to find 2 coterminal angles to negative 2 pi over 3. So we need to figure out, first of all, where are we going to be drawing the vector that creates all of these angles? In order to do that, I would, in your head, try to convert this into degrees. Does anyone know how many degrees 2 pi over 3 is? Right, yes, negative 120. It's negative 120 degrees. If you can't do it in your head, remember, we learned how to convert last class. You can, remember, put the radians on the bottom because you want it to cancel, right? So you have pi radians and then 180 up top, and then you can just plug in your calculator. It would be 2 times 180 divided by 3, which would give you 150 degrees. So now I can draw that. Negative 120 is how I think of it. 120 take away 90 because this first quadrant is 90 degrees. 120 take away 90 is 30. So I'm actually from this negative y-axis line, I'm going to be going 30 degrees more. So it's that line right there. Oops. And just to speed things along, I'll draw the exact same angle or exact same vector again right here. Okay, so now I'm going to be taking my angle, negative 2 pi over 3. And because it's in radians, instead of adding 360, I'm just going to add 2 pi. Now, what do I need to do first to actually combine these two terms? Right, yes. Right now you have a fraction plus a whole number. Right now they can't be combined. What we have to do is that second term, we have to make it a fraction with the exact same denominator as the first one. So what you do here is you multiply this by 3 over 3, creating 6 pi over 3. So then you're just adding negative 2 pi plus 6 pi, and you're getting negative 4 pi over. Oh, what am I doing? Did no one yell at me? Isn't it positive? Yes, it did. All right. So I know this is a positive angle, and 4 over 3 is not bigger than 2. So in my head, I know, okay, this is not going around twice like this one did, right? It's not going around twice because that number is not bigger than 2. So it's just this positive angle starting at the same initial side, going, now it's positive, so I go counterclockwise around to the terminal side, and I'm done. Would it be fine if we just did, yeah, and then converted it? You then need to convert it back into radians. So, but you can do that. Then we're going to take negative 2 pi over 3 and subtract 2 pi. Again, that subtraction of 2 pi needs to be converted into a fraction. It's the exact same fraction, negative 6 pi or 6 pi over 3, but this is a fraction. So negative 2 minus 6 is negative 8. So we have negative 8 pi over 3. So these are all conditional. I should probably search up saying. Now, this number, is this bigger than 2 pi? I mean, if you can't like think in fractions very well, it's fine if you even do 8 divided by 3. Is that bigger than 2? Yes, it is. Meaning, whatever angle you're going to be drawing is a full circle and then some. And this is a negative, so I know I'm going clockwise. So from my initial side, again, I know I'm going to be going more than once because it's bigger than 2 pi, bigger than one full circle, and I stop on the same terminal side, and I'm done. Does that make sense? You're always starting from that same positive x-axis. Right, because we're having to go clockwise. So we still have, like, you can think of it the same starting point, but instead of going counterclockwise this way, we're going clockwise. And the negative is what tells you that. So you can even write here, negative, so it's clockwise. This is positive, so it's counterclockwise. Well, there's a time when you would use the negative x-axis for the terminal side, like the ending side, or are you talking about the initial side? But if it's a 180-degree angle, yeah, the negative x-axis would be your terminal side for a initial, right? So the reason why I said sometimes you'll have the x-axis as your initial side, I was referring to what we're about to do way down here. You can think of that, this as having a negative initial side. Whenever it's asking about coterminal angles, and whenever it's giving you an angle in general, you're always, like a 30-degree angle or a negative 2 pi over 3, you're always going to assume, unless it tells you different, you're always going to assume that the initial side is your positive x. Okay. And actually, we've already talked about this next note. It says, can you have more than 3 coterminal angles? Can you have more than 3? Yes. How many? What's the max number you could possibly have? Is there any cap to how many multiples something has? Infinite, yes. There is no max. You can have infinitely many coterminal angles. Of course, we won't ask you for the infinitely many coterminal angles, but you can have as many as you can think of number of coterminal angles. For example, that 30-degree angle that we did previously, instead of adding just 360, you could add 2 times 360, which is just 750. Or you could keep adding. You could do another 750 plus another 360 and get 1110 degrees, etc. It keeps going. All right, so let's keep going. What time is it? What time is this then? 2, 2, so, all right. So on this next section, first we're going to do is we're kind of going to like define some variables so that we can then more easily find the answers to examples. You won't always have to use these variables. It's just good references. So what I want you to do is we're going to be given a point P, and it's on the terminal side of any angle. Point P is on the terminal side of any angle. So I'm going to draw an angle, creating a vector. We'll say like here. And I'm going to put a point P on that vector. And then what I'm going to do is I'm going to create a triangle with this point P. I'm going to draw a line straight down from point P to my initial side, to my positive x-axis, creating what is called, and I can't remember when we went over this year's been blurring together. Whoa. But we did go over what are called reference triangles. I'm not sure when we did it, but this is a reference triangle with the angle being closest to the origin is called your reference angle. They are references in terms of your point P. Now, because I drew that line straight down from P, this is actually a right angle. Because I drew it straight down, I know that that is the height of P. And height with a base, they're always perpendicular. So if point P has coordinates of x, y, this height that I just drew is the y value of point P. And the on the x-axis, the bottom portion of that right triangle is your x value of point P. And then we're going to call the distance from the origin to point P, we're going to call that r. And actually, the reason we're calling that r is because you can think of point P as being on a circle. So r is your radius. And we just use this Pythagorean theorem equation to find the value of r when we're not given r. So this is the equation we use to find the value of r. Knowing all this, we can define x as the horizontal distance of P. We can define y as the vertical distance of P. And r is the distance from the origin to point P. So sometimes knowing all this, sometimes it's super easy just to go right into an example and solve for values given point P. Like you can solve for the angle, you can solve for the distance, the r, you can solve for the x value, the y value. Sometimes it's really easy to go right into an example and start solving, but sometimes it's really hard to conceptualize exactly how to find those missing values. So that's why it's kind of good to know off the bat these your 6 trigonometric functions in terms of x, y, and r. So knowing that our theta is there by the origin, y is our opposite side, x is our adjacent side, and r is our hypotenuse. Why did I think we were done with trig? Oh my gosh, no. There is so much more to trig. You guys don't even have inkling of an idea of how much is left to learn about trig. But anyway, sine, what would my sine of theta ratio be in this triangle? Yes, O over H, Y over R. What about, whoa, that does not look like a Y. What about cosine? X over R, wonderful. What about tangent? Yes. And if you guys are still confused how we're knowing these, remember the acronym SOHCAHTOA tells you exactly where to put values in the trig ratio. Cosecant, the other three are just the reciprocal functions. So we are just taking sine and reciprocating it to get cosecant. You take cosine and find the reciprocal to get secant, and then take tangent and reciprocate it to get cotangent. Okay, so again, it's not really necessary to memorize these, but they are sometimes useful. Like that, it would be useful in helping you solve for example. But in example one, I am not, I'm not really going to be looking at this trig function to figure out my. So what it wants here is it wants us to find all 6 trig functions of this point if theta lies on the terminal side. So point P, I'm going to place on this coordinate plane. I'm going to create my lines in my graph really quickly. And I'm going to put point P on this negative 5 right here. And I'm going to draw my line going from the origin to my point. I really don't need to create a vector here. You can, but we're just trying to find the 6 trig ratio. So like, and then my line down to my x-axis. Oh, I drew those lines really off. Creating my reference triangle. I think I put them too close together here. 1, 2, 3, 4. All right. And this is point P. So I need to find my 6 trig functions, 6 trigonometric functions. I right now have absolutely no values drawn on this triangle. What values can I draw on this triangle? Yep, we know that this is a 90-degree angle right there. Why is 3? Yes, because this point, the value is negative 5, 3. And one more. Oh, you got it. X. Now, because this is a point, this bottom value is negative 5. If we instead had put 5, it would be like you were finding the trig values of this triangle, which is not what we drew, not what we want. It needs to be that negative 5. Don't drop that negative. So this problem right here is what I was referring to as you can have your initial side be the negative x-axis. This triangle is created as if the initial side is your negative x-axis. This is the only time that you would think of the initial side as being that negative x. All right, so let's find, well, can I immediately go in right now and find my trig values? Ah, think yes. How'd you get that? Pythagorean theorem, right. Okay. So also you can also just memorize that formula for R, but really it's just the Pythagorean theorem, right? We're finding the hypotenuse, which is always normally our C. Instead of writing C, I'm going to write R. And C is always equal to the square root of the other 2 sides added together. So this is 9 plus 25 is 34. Can the square root of 34 be simplified? No, no, it cannot. So we just leave it just like this, the square root of 34, sorry, 34. Your R value will always be positive. Even though this 5 was a negative, it squared and became, and yeah, you'll never have an imaginary number here is what I'm trying to say. All right, so now let's find our trig function. Sine of theta is equal to O over H. So that's 3 over square root of 34. Now, can I leave this like this? No, I need to rationalize the denominator, right? So you're going, and I'll write it out this first time in case we forgot how to do this. And I know some people just never understood how to do this and never asked, which is not good. Anytime you don't understand something, you should always ask. Anytime we want to get rid of the square root in the denominator, you just multiply by the square root over the square root. It remains in the numerator, but a square root times itself is the number inside. So that is what we end up with when we rationalize the fraction. Then cosine is A over H, whoops, which again, we rationalize. I'm going to skip writing that part because you really don't need it. You can know it's going to be negative 5 times the radical over the number inside the radical. Tangent is easy. It's 3 over negative 5. Forgot the theta. How could I? And then it's just the 3 reciprocal functions, which we find by not reciprocating the end answer. That makes our life harder. Instead, you're going to look at the initial one you found, because that would put the radical back in the numerator, and then I don't have to rationalize anything. So cosecant is square root of 34 over 3. Secant is square root of 34 over 5, and it's negative in total. And cotangent is negative. Wow, why do I keep forgetting theta? So again, they look like, I'm sorry that I'm making that, but the whole point in setting up trig functions like this with trig ratios is so that you can solve for the angle. Well, if you're really trying to solve for the angle, how many functions do you need? Just one. So it makes me mad that they make you set up all. You only need one. So I'm sorry. Sorry about this. Okay, I'm not going to do example 2, mainly because we really don't have time. But again, the reason why this is a little more tricky is because it lays along the y-axis, the negative y-axis, making it, and if you're good at conceptualizing, you can see in your brain what your opposite side is versus your adjacent side, but those things are hard to conceptualize. That's why it's more useful to remember these that we defined earlier in section 3. Okay. Did I record myself over this? Oh, I'm recording right now, so no. I do have this keyed out. I do have this keyed, and I will be putting it on Schoology. All right. So we're also good news. We're skipping this section because this is what we're going to be going over next class. So we're skipping this for now, learning it next class. I think that I am. So I think what I'm going to say. All right. So when we're looking at our coordinate plane, we've learned previously that the coordinate plane, x, y, and coordinate have 4 quadrants. quadrants 1 through 4, and you label them in the shape of a C, right? So if you're thinking about a C, you're going to start in the top right quadrant. That's your quadrant number 1. And you go around in a C shape. This is 2, then 3, then 4. That's how you always remember the quadrant on an x-axis coordinate grid. Now, also good to know is which trig functions are positive. C is for quadrant. Yeah. You can know which trig functions are positive in which quadrants. Depending on which quadrant you are, changes which trig functions are positive there. And the way that you memorize this, the acronym, now there are a couple of acronyms that go out there, but the main one that everyone learns, I learned way back in high school, and this school uses as well, is all students take calculus, which is not, but that's all students take calculus. Now, what this means is in your quadrant number 1, all of the trig functions and their reciprocal functions are positive in quadrant 1. Everything that we've been doing in right triangle trig has been assuming that those triangles are in quadrant 1, basically. Everything we've been doing so far has taken place in quadrant 1. Now we're learning that there are trig functions in different quadrants, 2, 3, and 4. So in quadrant 2, only sine and its reciprocal are positive. In quadrant 3, only tangent and its reciprocal positive. And in quadrant 4, only cosine and its reciprocal are positive. All students take calculus. This is one of the things that has been ingrained in my brain and will never leave, just like self-control. All students take calculus. Now, there's many ways it's used, but one of the ways that it's used is when it literally asks you determine the sign plus or minus of the intervals and ratios. So here in our interval from pi to 3 pi over 2. So if I'm looking at this x and y axis over here, I know that pi is the same exact thing as 180. So starting from that initial 0 degrees, which I have as my positive x-axis, my pi is way over here on the negative x-axis line, right? That's 180 degrees if I'm starting at 0. And then 3 pi over 2, that is the equivalent radian for 270, which is the bottom line. Why do I keep saying 2? It's 3 pi over 2. This is the hardest one to remember. But honestly, it is one that you're eventually just going to have to memorize because it's just going to be way too much. You'll be converting 270 into 3 pi over 2 way too often to actually convert it every time. It's just like you remember pi is 180 and 2 pi is 360. 3 pi over 2 is 270. And also, good to know. Whoa, whoa. Oh, I'm still on pieces. That's why. Good to know is that this top line is pi over 2, 90 degrees. These are the 3 most known radians. Pi over 2, pi, and 3 pi over 2. Just like 90, 180, and 270, you probably haven't done it. You will. Okay, so the interval from pi to 3 pi over 2 is this. It's asking in this interval which trig functions are positive. trig functions are in the interval from pi to 3 pi over 2? Yes, tangent and its reciprocal cotangent. Which trig functions are negative? Everything else, literally everything else. So sine and its reciprocal cosecant, cosine and its reciprocal secant. So now this is the most straightforward that you're going to apply which functions are positive where. Like it'll literally straight up ask you which ones are positive here. Or, and I'm only going to do one of these. I have my answer key showing the other, but I'm just going to solve for one. Or it's applying that knowledge to other problems. So here it says find the other trig ratios given one of the ratios. So it says find cosine of theta and tangent of theta given that sine of theta is 3 over 7 and tangent of theta is less than 0. So if I didn't apply what I just learned about different trig functions, different quadrants, I would think that I was just, and don't draw it, I would think that I would just be drawing um, this, right? Because, okay, those are two positive numbers. Yeah, I'm just going to draw it there. However, this second part tells us that tangent of theta is less than 0, meaning tangent is negative. So we have to think, where is sine positive? Because sine is positive there. 3 over 7 is positive. Where is sine positive and tangent negative? In quadrant 2. Oh my gosh. So we know we would have been totally wrong if I didn't think this through, and it would have affected all of our trig functions. So I'm going to draw my x and y axis, but I know I'm going to be drawing this in the second quadrant, so I'm going to be putting more room in my second quadrant. And I'm going to be drawing my line that creates my angle, theta, and it's 3 over 7. So I know that 7 is my hypotenuse and 3 is my opposite. So I'm going to make that 7 much longer than my opposite side would be. I'm just explaining how I'm drawing it. Does your picture need to be drawn perfectly to scale? No. The reason why it's called a reference triangle is because it's for your reference to solve the problem. So as long as you know what you're talking about, it doesn't matter. I'm just not picky grading, but picky with myself. All right. So what values can I put where on this triangle that I drew, this reference triangle? Yes, 3 is my what? 3 is my opposite side across from theta. What else? 7 is the hypotenuse. Yes. So can I immediately find cosine and tangent here? Not immediately because I don't have the side. So what do I have to do? Pythagorean theorem. So I'm missing a leg this time. So what I'm going to do is I'm going to square root the hypotenuse squared minus the other leg squared. So that's 49 minus 9, which gives you 40. Can this be simplified? How so? What can you pull out? Right, 4. I was about to say the perfect square that goes into 40 is 4. So you pull the square root of 4 out, and you still have times the square root of 10. The square root of 4 is 2. So you're left with 2 times square root of 10. If that confused you, it's fine. This is what. So remember that when we're actually square rooting something, which I did actually square root that 4, right? When you actually square root, you can end up with the plus or the minus version of 2 square root. What this means is you need to look at your reference triangle and determine which one is true in this case. Do I have the positive 2 square root 10 or do I have the negative 2 square root 10? Negative. This is why the position of your reference triangle matters, because if we had drawn it on the other side, we would have assumed that this bottom number was positive 2 square root 10, which it's clearly not. So then, now I can, what did it want? What did it want? Cosine and tangent. So cosine of theta is negative 2 square root 10 over 7, a over h. And tangent is over a. Of course, they had to be difficult. So I can't leave this tangent ratio as is because I have a radical in the denominator. So I'm going to multiply both the top and the bottom by the square root of 10, and you end up with 3 square root 10 over negative 2 times 10, or negative 20. No, R will not ever be negative because you can technically think of all of, because we're drawing this on the coordinate plane, you can think of the edge of that R as being the edge of a circle, right? Where R represents radius. You are never going to have a negative radius. That would be an imaginary circle. You can't have a negative circle, a negative radius in a circle, right? So R will always be positive, always. All right, so that's it for these notes. That's all I wanted to show you. Are there any questions?